Hello everyone, my name is Dr. Sunil Dahire. I am Associate Professor in Dada Ramchand Bapu Sindhu Mahavidyalaya. We are discussing crystal field theory. In this section, we will discuss absorption spectra of complexes. It is observed that most of the complexes are colored. So, this is advantage of crystal field theory. By using crystal field theory, we can explain color properties of complexes. Any substance appears colored if it absorbs visible light. The complexes are colored because they absorb visible light. Absorption of visible light by complexes can be explained with the help of crystal field theory. Crystal field theory considered splitting of d orbital in lower and higher cell. The energy difference between lower d and higher d orbital is known as crystal field splitting energy. The crystal field splitting energy is nearly equal to the energy of visible light. Therefore, complexes absorb visible light and electrons which are present in lower d orbital undergo excitation from lower d to higher d. So this electronic transition is also known as dd transition. During dd transition, absorption of visible light takes place and therefore complexes appear colored or they show colored properties. To understand absorption spectra of complexes, we should know selection rules for electronic spectra. So there are two selection rules, Laporte selection rule and second is spin selection rule. So let us see these two rules one by one. First rule is Laporte selection rule. According to Laporte selection rule, electronic transition takes place if parity of molecular orbital is changed. Electronic transition takes place if parity of molecular orbital is changed. It means that if electron excite from 1g to u orbital or u to g orbital, such type of electronic transitions are allowed. But if electron excite from G to G or U to U, in that case, such electronic transition is forbidden. In these electronic transition, parity means symmetry of orbital is not changed. Therefore, such electronic transitions are forbidden according to Laporte selection rule. Second rule is spin selection rule. According to spin selection rule, electronic transition is allowed from, say, when the multiplicity of orbital is same. It means from singlet to singlet or triplet to triplet, such type of electronic transitions are allowed. So these two rules are important to understand absorption spectra of complexes. So let us see absorption spectra of TiH2O6 times 3+. This is hexaquo titanium 3 complex ion. This complex ion is an example of D1 system because in this complex central titanium, atomic number of titanium is 22 and its configuration is 3d2 4s2. This is outermost configuration. In hexaquo titanium 3+ complex, oxidation state of titanium is +3 and hence it loses 3 electrons from outermost shell. The configuration becomes 3d1. Therefore, this complex is an example of D1 system. When there is one electron in d orbital, this electron first occupy lower d orbital. This electron absorb visible light and undergo electronic transition from lower d to higher d orbital. During this absorption of light takes place, and the absorption spectra of the electron is like this. So this is the actual absorption spectra of hexaquatitanium 3 plus complex. From this absorption spectra, this absorption spectra can be explained in 4 parts. First part is position of the band. Second one is intensity of the band. Third point is intensity of the band. And fourth one is symmetry of the band. Actually, it should be width of the band. Width of the band. So absorption spectra of titanium H2O6 times 3 plus can be discussed in these 4 portions. So let us discuss one by one. First point is position of the band. From this spectra, we can see that position of the band means absorption band occur at 500 nanometer, or in terms of frequency, it is 20,000 centimeter inverse. So these are the frequency values in centimeter inverse, and these are lambda values, wavelength values in nanometer. In terms of wavelength, position of the band is 500 nanometer and frequency of the band is 20,000 centimeter inverse. And this absorption takes place due to electronic transition from lower d orbital to higher d orbital. Second point is intensity of the band. Intensity of the band is from the spectra we can see that intensity of the band is only 5, means epsilon. This is the epsilon value. Epsilon means molar absorptivity. Molar absorptivity of the band is only 5. Only 5. Normally, when transition is allowed, the molar absorptivity is in the range of 10 to the power 4. But in this case, it is only 5. This indicates that this transition is not allowed. This transition is not possible. It is not allowed, and it can be explained by Laporte selection rule. According to Laporte selection rule, only those transitions are allowed in which parity means symmetry of molecular orbitally change. G to U or U to G are allowed. In this transition, one electron excited from lower d to higher d. Both d orbitals, they are in octahedral geometry. Both d orbitals, they have same symmetry, and according to Laporte selection rule, transition from one centrosymmetric to another centrosymmetric orbital is not allowed according to Laporte selection rule, and due to forbidden transition, intensity of the band is very low. And third point is width of the band. As absorption takes place, the band should be sharp. It should be like this, sharp. But we can see that the band is not sharp. It is broad band. Wide band is there. And this wide band is due to presence of in this electronic transition. This electronic transition is accompanied by vibrational excitation. This electronic excitation is accompanied by vibrational excitation. Due to these two excitation, electronic as well as vibrational excitation, nature of band is wide. If there will be only electronic excitation, in that case, band would have been sharper. But in this case, the nature of band is wide due to the fact that electronic excitation is accompanied by vibrational excitation. Then fourth point is symmetry of the band. We can see that in this spectra from both sides, the band is not symmetrical. Band is not symmetrical means the band, unsymmetrical nature of the band can be explained with the help of John Taylor effect. In John-Taylor effect, we have discussed that this effect takes place when T2G or EG orbitals are unsymmetrically filled. In TiH2O6 3+ complex, so it is an example of D1 system, and for D1 system configuration will be T2G1 EG0. As T2G orbital is unsymmetrically filled because there is only one electron in T2G orbital, in this case John-Taylor effect takes place, and according to John-Taylor effect, EG and T2G orbital further split into two orbitals, and due to further splitting of these orbitals, we get two types of electronic excitation from T2G, lower T2G to EG and higher T2G to EG. These two electronic excitation, due to these two electronic excitation, the absorption band is not symmetrical because this band is combination of these two electronic excitation. Therefore, nature of band is not symmetrical. So this is all about absorption spectra of titanium H2O6 times 3+. Similarly, we can explain absorption spectra of Cu H2O6 times 2+. In this complex, this complex is an example of 3D 9 system. There are 9 electrons in d orbital. The only difference is in this complex, instead of electronic transition, excitation of hole takes place. That is only the difference. The rest, the absorption spectra, nature of spectra is somewhat similar. So this is all about absorption spectra of complexes. Thank you.